Okay, let's now talk about the Kubernetes objects. Kubernetes objects are persistent entities on the cluster system that are used to display the cluster state. They are configured using the YAML file and are pretty much determining what applications are using the containers and what is the node that the containers are running on. They also determine the resources available for those applications and the processes and the rules associated with the applications. So Kubernetes verifies that an object exists and functions when it is formed in the cluster. So the specification of a cluster describes the desired state, the features and the configuration that you want to have on the object, while the state, for example, describe the point at which the object is in the current moment. Both of those factors are supplied and updated by Kubernetes to ensure that we have the correct state at all times. So due to the large amount of information that is usually associated with each deployment, it is not convenient to do the configuration directly using commands. For that reason, we're using this YAML file that consists of the data that you can see in front of you. And specifically, this YAML file is taken from nginx web server and it is specifying two replicas of nginx web server running inside two containers. So here are the key points for running the YAML file, which are the specifications for the applications that are running into the container and the nodes they run on, the resources available for the application, and the policies and the rules, as we mentioned. So there are actually three main fields that I want you to pay attention into the YAML file, and those are the API version, which pretty much specifies which version of Kubernetes API we're using to create an object. Then it is the kind, and the kind means the type of object that we want to create. And finally, it is the metadata, which is a single piece of data that allows an object to be differentiated by including string of characters such as name, ID, and so on. So let's have a look at some of the main components or objects from Kubernetes that you need to know. Now, one of the most important objects that you need to understand are the pods. So this is one of the Kubernetes fundamental unit. This is the smallest and the most basic drop-down object in your model, and so the pod contains a software container, storage resources, and network resources to support that container. Then the next object are the controllers, and those objects create and manage multiple pods. They handle replicas and provide automatic repair capacity. For example, the controller can automatically replace a scheduled pod on the node with an identical replication on a completely different node if the first one fails. There are different types of controllers such as deployment, stateful sets, and daemon sets. Then we have the service object, which is an abstract way of offering network service for an application that is operating on a number of pods. So Kubernetes can assign a set of pods on their own IP address and daemon name and balance the complete load between those services. So the presence of services is normally motivated by the fact that pods in Kubernetes have a finite life cycles. Kubernetes provides name resolution of the services within the cluster in addition to the IP address assignment to them. So we will be able to communicate among the pods using the names of the previously enabled services in this way. Then we have the ingress object that provides externally accessible URLs, load balancing, TLS termination, and name-based virtual hosting to Kubernetes services by exposing the HTTP and HTTPS routes from outside the cluster to the Kubernetes services. So in real life, the ingress is simply used to expose HTTP and HTTP ports to the world so they can access your application. And the other final most important object is the ingress controller, which deploys a container into a pod in a cluster. So there are several load balancing system providers such as HA Proxy or nginx, and both of those define their own ingress controllers that you can use. So all the objects of Kubernetes normally consist of metadata, a specification, and a state. You must interact with Kubernetes API by providing metadata and the spec in JSON format within the required field in order to create an object. The most typical method is to create a command line client such as kubectl, to which you can supply a file into YAML format and then transform to JSON in order to make an API request. Now, since I mentioned that one of the most important components in Kubernetes are the pods, let's talk a little bit about them. Now, the pods are actually the smallest deployment unit in Kubernetes. You can also specify pods with many containers, which forces those containers to be deployed in the same node at all times. This is quite useful if the containers communicate over the file system. So here you can see the different components of a pod. It has a volume, file pooler, web server, from where we can update it to the customers, and from the content manager. So normally containers are inside the pod and they have access to its network and storage resources. In terms of network, each pod is assigned to a unique IP address, and each container uses the same network, both IP and ports. So if you want to define a container within the pod, you can use the name of the pod to identify it within the cluster, the image of the container to be displayed, so you can pretty much define the name of the container using an image key. We can also specify a list of variable names and values that will be injected into the container as environment variables using the standard env form key for Linux, for example. You can also define containers using a list of ports that are used by those containers. Then you can add a pull policy, which is a container unloading policy. For example, we can indicate that it always pulls the container image before deploying it. You can also add reserve and resource limits. We can always define reserves in the resources such as RAM or CPU using the resources key, and in that way we can also define limits. Also, using readiness, you can find out when a container is ready to serve traffic after it's been started and if it is still ready for this task. So in order to specify the structure of a pod, you can use the YAML format, and for example, again I will use the ng INX library. So here you can see that we're defining the kind, that is pod. You have the API version, and then you have the metadata for the pod. For example, the name of the metadata is AGINX. You can define namespace and labels. So each existing pod contains of needed application, storage resources, IP address, and other container-specific parameters. In Kubernetes, a pod represents a single instance of application, which might be on one or more shared containers. So we should always remember that all the containers into a pod share absolutely the same IP address and are accessible from the local host address as well. So a pod cannot recover by itself when it dies for some reason. The Kubernetes controller decides whether to create a new one to meet the total number of pods that are desired by user. For storage, each pod can specify a shared storage that all existing containers can access and share the necessary data. The volumes created can be persistent to save the necessary information even if the pod has to be restarted. Also, when a pod is being destroyed, all the information inside that pod also gets destroyed. So for that reason, we really have to use volumes in order to be able to create persistent applications. And we really need volumes because the files on a disk related to containers are all running inside various pods that are not recoverable. And of course, this creates two main problems. The first one is that the container is restricted when it stops its execution, and the second one is that it's usually necessary for two containers running simultaneously in the same pod to exchange information. So you can see here on the figure in front of you how the clusters are working and how you can define volume for two particular containers. So you can think of the Kubernetes volume as a directory of various containers within a pod that can save the same information. And as you can see on the right side, there are some different main types of volumes that are normally used. And the first one is the empty dir. This is a basic type of volume, and this is created when a pod is first allocated to a node. So it starts out as an empty directory, and then the containers will fill it with necessary data. This volume will be active as long as the pod that is contained within that volume is also active. And also the data will be finished once the pod is finished as well. The next type of volume is called the NFS volume, and the NFS will let you mount an existing network file system that is shared on the pod. When the pod completes its execution, the volume is dismounted rather than removed, which allows the information that it contains to be assessed by other pods at the same time. The other type of volume is called persistent volume claim, and this is used to mount a persistent volume, which is a way to use stored space in a durable way. And the final type of volume is the secret, which is used to pass confidential information such as passwords, access codes, or tokens to the pods. They are stored in a key value pair format using the TMPFS database that we talked earlier about. Now, another topic that I want to talk about are the deployments. You can find the deployments into this page right here into the Kubernetes website, and they use replica set, which is in charge for controlling the number of pods and their allocation between the different nodes. So you can see a YAML file of ng-inx pods, and here you can see that the kind is the deployment, you can see the API version and so on. Now, there are a few main components of the deployment. Those are the name of the deployment, which is the name with which the deployment will be identified. Then you have the deployment tags, where we will be able to define labels to be able to reference the deployment. Then you have the number of replicas desired, which is obviously the number of replicas needed for the pod that we want to deploy. Version history to control the version, and upgrade strategies, which are some set of specific strategies used during the deployment. Another interesting feature of Kubernetes are the replica sets that ensure that the number of replicas of a given pod is always executed within the cluster. This will ensure that our pods are always available. And here you can see the YAML file of that object. Kubernetes uses kubecontroller and kubescheduler services to do replica sets. So for example, if a deployment specifies that it needs 5 replicas of a pod, a replica set will ensure that there are always 5 active replicas in that cluster. So the services are another important object into Kubernetes, and a service in Kubernetes is an abstraction layer used to route traffic to the corresponding pods. It is not necessary to find IP address for each of them, whether they support TCP or UDP protocols. So labels are commonly used to define which pod should be routed, so the service simply needs that label to match regardless how the pods were formed. So here on the figure in front of you, I will draw you the basic scheme for executing the Kubernetes services, and you can see they have several components such as client, cluster IP, API server, and kube proxy, which is connected to the backend pods. So the cluster IP, which is in this cloud here, is the default service type and exposes the service with an internal IP to the cluster. This means that the service will be accessible only by objects inside it. If you notice here, we have the node port, which exposes the service to each node using the node IP address and a specific port, in that case 9060. This creates automatically cluster IP service to which the node port service is routed. So the service can be accessed from outside the cluster using the node IP and the port IP path for exposing the node. You also normally have load balancer that exposes the service externally, and it uses the node port and the cluster IP to follow the path between the pod and outside world. So we already talked about the replica sets that are intended for pods that have the same state and so can be exposed to the Kubernetes using the same IP address with a load balancer between them. There are also another type of sets that are called stateful sets that have completely different approach. So the question is actually what happens if one of the pods replicates the application deployed and have different status than the rest. So in this case, we cannot go to any of the pods under a single IP address with a balancer. So here the idea is to manage the application where those imperfections occur. So for that we're using the stateful sets that are intended for pods that require unique network identifiers, persistent storage, ordered development, or upgrades within a certain order. So in that case, pods maintain unique identifier that persists even if they are reassigned to other nodes. So since now you know how Kubernetes service works, let's talk about the Kubernetes networking model. So the decoupled microservices-based applications rely heavily on networks to mimic the right coupling that's available. Networks in general are not the easiest to understand, so Kubernetes is really not an exception because it basically needs to address four main networking challenges. The first one is the container-to-container communication within the pods that needs to create an isolated network space for each container that starts with the help of the kernel features of the underlying operating system. On Linux, for example, this isolated network space is called a network namespace, and it is pretty much shared between containers or with the host operating system. So a network namespace is created within the pod when a pod is started, and all containers running within the pod will share that network namespace so that they can communicate via the same local host. The other challenge for the Kubernetes network is the pod-to-pod communication through the cluster nodes. So as you know, pods are assigned to nodes in the Kubernetes cluster in a random way. So they should be able to connect with all other pods in the cluster regardless of their hostname, and all without the use of network address translation or NAT. And this is very important rule for the Kubernetes-based network implementation. In this case, Kubernetes network model aims to reduce the complexity and treats the pods in the same way that it treats the virtual machines that are on the same network. In that case, each virtual machine receives an IP address, so in the same way each pod also receives a separate IP address. So this model will ensure pod-to-pod communication in the same way in which the virtual machines communicate between each other. And the final challenges are the external communication from the pod. So a successful deployed application running on pods within Kubernetes cluster also requires accessibility to and from external network. In this case, the services are processed to encapsulate network rule specification in the cluster nodes and are used by Kubernetes to provide connectivity in this situation. The apps become accessible from outside the cluster using a virtual IP address after using the kube proxy to expose the services to external networks. So this will be the final slide from this video, guys. Thank you very much for watching. We covered quite a lot from the Kubernetes based architecture and object. And in the next video, I will show you how you can deploy Kubernetes in your device and run clusters. Thanks for watching. Now let's